So what is deep learning? Deep learning is about using a deep architecture in which we have several hidden layers in the neural networks. So it's a series of hidden layers with nonlinear operations between the input and the output. So we allow to have several hidden layers because this will allow to actually tackle very complicated domains, very complicated kind of data where we don't have simple functions, but really data like videos and images and text, etc. Why the term deep learning or deep architecture? It is used to contrast it with the shallow architectures. We have seen several machine learning algorithms in this course. By shallow, it means that we are not combining the features beyond the first or second or third level. In other words, things like the perceptrons, like k-nearest neighbors, etc., use simply the weighted sum of WIXI, and we use the sign of this to make the classification. So we don't go beyond really combining those features once or twice or three times. But the idea of neural networks and deep neural networks is really to go beyond, to build extra and more and smarter features from the data. The principle of deep architecture is as follows. So we use a series of layers between input and output, right? But we want these layers to be able to learn features or to learn hierarchy of features identification at different levels. So we're going to have a better and better granularity of the features. So this is by excellence used in vision. If we have an image of pixels and we want to be able to actually recognize what's in the image, so for the computer it's just a bunch of pixels, of pixels with some color for each pixel. So achieving the high level representation of saying that this picture is actually a man and a woman dancing or maybe holding hands, we're going to go through a process of putting that data over several layers to extract the features. In other words, we're going to leave the network detect the features by itself, which lead to an automatic detection or abstraction of the data. So we're going to learn higher and higher levels of features. So we start with the pixels. So what's going to happen here for the vector representation is so we have pixels here, right? So these are, these dots. So I'm going to put them in this vector. So obtain a very long vector representing the image as input. For the computer, again, it's just a bunch of pixels. There is no meaning to the pixels in this image. So a first layer of hidden layers in the network will have a slightly higher level of representations of abstraction. So I'm going to maybe identify the edges in the pictures, the corners, etc. So I'm going to identify, for example, that there are some horizontal lines that represent the shirt of the boy or the man in the picture. We're going to have maybe some horizontal line representing the hair, etc. Maybe some borders representing the mouth, etc. So I'm going to present a slightly higher, so going from the pixel to larger components. Then a second layer will have even higher level of representations in which we are going to identify the eyes, if there is a nose, the hair, maybe the mouth, etc. So I'm going to each layer be able to detect automatically new features from the image. And at the end, coming to the sentence, man and woman dancing is really the highest possible level of representation that would actually help tag images, the hundreds of thousands of images that we can find online. Okay, so the idea is to, this is very important, is to use hidden layers to act as feature detectors. We want to detect the features by ourselves. For many, many years in vision, we have been actually creating these features either manually or with some algorithms. We are going to go through the image in pixels and get these features ourselves or with some algorithm. But today we want to be able to, through this set of layers, be able to allow the network to detect those features for us. We don't have to hard code them or to curate them or to craft them. They are actually detected by the training of this kind of architectures. This is truly a revolution, and this came from an inspiration, again, from biology. So basically, you know that in AI, many things are inspired by biology. Remember genetic algorithms, remember the perceptron. Here again, according to some recent research on the visual cortex, researchers found that actually the visual cortex is a hierarchy of 5 to 10 levels for the visual system. So this is pretty powerful because it says that human vision, which which is actually very something that came with us. We don't make any effort to see and detect objects in our scene that we are watching. So basically, we discovered that human being is also doing it in phases, and this is what actually inspired the use of deep architectures today. So we know that to build neural networks, we need to learn the weights. So we have the architecture, we build the weights. A question is, multilayer neural networks have been there for a few decades, and we know backpropagation, right? But why is deep learning so revolutionary today? And the answer is that we know how to learn the weights with one hidden layers. As we add more layers, it becomes harder and more computationally expensive to do it. So the novelty of this neural networks with deep architectures today is that actually we have today new algorithms for learning these kinds of ways for this kind of architectures. I would add to that that actually we have lots of data, right? So these are algorithms plus data plus also computational power. So we can compute faster. We have way more data than we had in the 90s. And now we have smarter algorithms that know how to train neural networks with several hidden layers, as opposed to backpropagation that works only for one hidden layer. The hidden layers make sense. Observe this set of digits, handwritten digits that I wrote myself. So what kind of features make sense to you? So we could, observing this data, we could think that actually it's possible to detect some features at different granularity levels. For example, we could detect that there are bars. So whenever there is a possible horizontal or vertical line, we could detect that. So this is a kind of features. We could also think about horizontal bars. I'll put that with another color. So we'll have other horizontal bars. So these are kind of a high abstraction that goes from actually the level of the pixel to the level of lines. Okay. So you could also detect maybe the loops. For example, this loop. This is a bigger loop, etc. So it could focus on these kinds of components. For the eye, it's natural. So we see bars, but we know how to decompose these images. But for a computer, it has to learn how to detect those kinds of features automatically. So more concretely, suppose we have digit 3 that is digitized or pixelized. So we have here the pixels for number 3. Again, the computer doesn't see 3, it sees pixels, right? So we're going to turn that into a set of a very tall vector of pixels. So suppose this is what actually the focus for neuron 1, neuron 2, neuron 3, etc. So what can happen is that so we have this line here that could be maybe in this area here. This area will actually fire this neuron here. So this neuron will actually basically learn this horizontal line here. Then we could do the same thing. This second layer will learn the second horizontal line, and so on and so forth. So depending on which actually weights are higher for the connections between, so we have all connections, but some of them will be highlighted more than others. And those are highlighted more than others actually will define which kind of area in the image is being encoded by this neuron here. Okay, so some areas will focus on these lines. Others will probably focus maybe on vertical lines or other kinds of parts of the image. All right, so then we are going to combine that higher. So at a higher level, we are going to have a bunch of lines. We're going to have a bunch of other features of the object, and so on and so forth. So by putting the data in as input and looking at the weights of those features that are going to the next neurons, what we can, by learning, highlight subparts of the image. Despite the advances with computation, with data, and with algorithms, deep neural networks remain very hard to train. And the reason is that we have too many connections between the neurons in the network. We are talking about here fully connected neural networks with many hidden layers. So we need to somehow relax this connection so as we are able to do the learning on this data. So it turned out that one variant of neural networks with deep architectures, with this variant, we can actually achieve closer results and have a good approximations. And this is called convolutional neural networks, or CNN, which has a fewer connections and parameters. So this is also inspired by the visual architecture, but in which we have 5 to 7 layers, which are hard to train with the plain deep neural network. Okay, so with CNN, even though we relax the connections, we're going to have an easier time to train, and it has an even interesting performance, even if it's slightly less performing than deep neural networks. An example of such systems is LearNet5 from LeCun, developed in 1998. So you could check out this reference here, this article. There's also a demo online on Yann LeCun's webpage, in which you show that actually we have a CNN in which you have different these different layers. He represents only parts of the layers here. And you would see digits passing through this screen and being recognized pretty much right away. So this is the prediction, and this is the image of the digits. So this is one of the systems that actually has been showing really very, very good performance on recognizing digits for envelopes or also for ATA machines. Nowadays, we also see many very interesting software for deep learning and very advanced ones in several languages. So these are the main four I know. That's Torch, scripting in a very specific scripting language called Lua. We also have Theano, developed in Python. There is a full suite for vision called Café. And finally, a very popular tool in Python developed by Google is called TensorFlow that you could also check out online. All right, so I recommend this tutorial on deep learning that you could actually use to complement your knowledge. I gave you just a flavor of what are deep learning, but I just wanted to emphasize that this is the future and they seem unstoppable. The progress that we have seen in the last last decade and last few years has been incredible in machine translations, in handling text, in doing image vision and vision understanding. It's pretty actually amazing what deep neural networks are capable of doing, and we would expect actually a lot more progress now that it's becoming very popular.